This is a lesson on common ion effect and buffered solutions. If you have an equilibrium, say hydrogen fluoride, which is weak acid, falls apart to make H plus F minus. If you have an equilibrium and you dump in some sodium fluoride or some other aqueous salt, what that does is it increases the amount of fluoride. This is large because it's a weak acid. Therefore, the equilibrium shifts to the left, decreasing the acidity and raising the pH. So this is a common ion effect. If you would put in some sodium chloride, it would not affect, because chloride is not F, so it wouldn't affect anything. Same thing can go for bases. If you have equilibrium NH3 plus H2O, equilibrium NH4 plus OH minus. If you put in a whole bunch of, say, ammonium bromide, that would increase this. This is large because it's a weak base. Weak bases don't ionize very well. Therefore, the equilibrium will shift again to the left, decreasing the amount of hydroxide. This is also the effect when you had polyprotic ions. You have polyprotic ions, you have HCO3 minus, you have the common ion, in this case is H plus. When this H falls apart, it increases that, shifting it back, so you don't get very much CO3 minus. Your base calculation with a common ion solution. In the past, what we've had is we've only had one source of compound, and that would be the weak base or weak acid in itself. So in this case, if you have 2 molar hydrofluoric acid, where you have a Ka of equal to 0.00072, mixed in with a 1.0 molar solution of sodium fluoride, what would be the pH? Well, in the past, all you've had is the HF equilibrium, H plus F minus. This is 2.0 molar. And in the past, this has been 0, and this has been 0. But now, this is 1.0, because you have 2 different sources of it. So they're not X and X anymore, it's 0, 1.0. You still do the ICO the same way. You subtract X here, add X here, because you got to get it bigger than 0, and add X there. 2 minus X, X disappears, X, 1 plus X disappears. So you get 0.00072 times, or equals, H plus times 1 divided by 2.0. H plus is equal to 0.00144, and the pH is equal to 2.84. What we have on a buffered solution is a situation where you have a common ion and its conjugate base or acid. So you got a weak acid and its conjugate base, or you got a weak base and its conjugate acid in solution, so that your amounts of H plus or OH minus is really small. And then in that case, adding any acid or base will not change the concentrations very much. So a buffered solution occurs when you mix a weak acid and its conjugate salt, or a weak base and its conjugate acid. Either one of those two will work. Examples, if you have a weak acid of HF, the conjugate salt could be KF, NaF, NH4F, as long as it contains an F. The weak base, say NH3 is a common one. The conjugate acid, salt, conjugate salt, NH4F, NH4NO3, doesn't matter as long as it starts with NH4 and it ionizes completely. So those would be examples of buffering pairs, things that can be made a buffer out of. To calculate the changes in pH, step 1, use stoichiometry. To calculate new amounts. To eliminate the added acid or base, depending upon what the stuff is, to find new amounts. Of the weak acid or base and its conjugate base or acid, whichever one it is. Care must be taken to make sure you have things in units. Everything has to be in moles, or everything must be in molarity. You cannot mix molarity with moles, and that's where people get messed up oftentimes. Step 2, you do your equilibrium expression. To calculate new concentrations. Now, technically, it's best to do moles for stoichiometry and molarity for down here. It really doesn't matter which one you do, as long as you have equal amounts of solutions. If you don't have equal amounts of solutions, then you do have to make sure this is moles and this is molarity. first example to the previous example up here, you have, you want to know the pH. If 0.10 moles of solid NaOH is added to 0.50 liters of previous solution. Okay, so there's two parts to this, remember. You got, since you're adding an OH, a base, you're going to be destroying the acid. In the equilibrium expression here, this is the acid, and this is the conjugate base. And it's very important to know which stuff you're attacking. The base will attack the acid in this case. So the NaOH will react with the HF to produce your F minus plus water plus sodium ions. Sodium ions, you don't care. So water, you don't care. So originally, the moles of NaOH is 0.10 moles. HF, up here in the original condition, is 2 molar. But 2 molar is not moles. You cannot have moles and molar. That's the real bugaboo that you can't do. So you can change the moles to molar or the molar to moles. So it doesn't matter. Let's change it to moles. So you got multiplied by 0.5 because molarity is moles divided by liters. So multiply that by that. That's 1. This number, again, is 1 times 0.5. And that will give you 0.5. Those two don't care. You eliminate all of your added acid or base. So this is just the stoichiometry part. That eliminates down and you get 0.99 and 0.51. Now you can go back up to your equilibrium ice table and do the equilibrium part. So the first part is stoichiometry, eating up any strong acid or strong base you add. Next part is your ice table, equilibrium table. And you go back to the original expression up here. HF, equilibrium, H plus F minus. HF in this case is 0.99, but that is in 0.5. This is 0.9 moles. Remember, we changed the moles. When changing liters, you got to divide by 0.5, which would be 1.98. This, for all practical intents and purposes, is 0. This divided by 0.5 is 1.02. Add x, subtract x because it's a 1-to-1-to-1 ratio. This turns out to be 1.98. X, 1.02, ignoring the plus x and the minus x. Plug that into the equation. 0.10 0.00072 equals the hydrogen ion times the fluoride, which is 1.02, divided by 1.98. Do the math. The H plus turns into I don't have the H plus concentration, but the pH is 2.85. So adding that much base changed the pH 0.01 mole, 0.01 for the molarity. Now, what would have happened if we would have had just the acid? Just put, here's one example. Another example, what would happen if you put 0.01 moles of solid NaOH in water? Well, it ionizes completely, so the OH concentration is 0.010. Take the negative log of that, and you get 0.0, that's divided by 0.5 because it's in 1 liter, so that divided by that is 0.02 molar. Do the negative log of that, you get 1.6, that's the pOH. So the pH is 12.3. So it went from 7 pH neutral water down to that, or a difference of 5.30 pH. Adding the same amount of base to a buffered solution, and it changed 0.01. So it changed 0.01 compared to 5.30. That is the big benefit of adding buffered solutions. The last part I want to go over is the same situation as before, but in this case we are going to add 0.020 moles of concentrated hydrochloric acid. Before, up here we added a base, now we're going to add an acid. Pretty much the same thing. We're going to add it to 0.50 liters of the stuff, assume no volume change, is what we're going to have to do there. We are adding an acid, so it's going to react with the base, and in this equilibrium, the base is the F minus. So it's going to be F minus plus HCl makes HF. The F minus 1.0 molar. Is that right? 0.5, sorry. 0.5, because you got to change it to moles. 0.02. And let's see. The HF is 1. So that's correct. Subtract 0.02 minus 0.02 plus 0.02. So the stoichiometry part, 0.48, 1.02. Now we got to do the ice table with the equilibrium part. This is still written the same way because that's the way you write the Ka. You do right over left. So the HF is 1.02, practically 0, 0.48, plus x minus x, 1.02, practically, x, 0.48, practically. Set the equilibrium expression, 0.00072 equals H plus times F minus, which is 0.48, divided by 1.02. Solve for the equation, and you end up with a pH of 2.82, which is a very small change again. That ends this initial lesson on adding acids and bases to acidic buffers. We'll continue on with more examples on basic buffers and buffering capacity, which will be coming on last.